anything?
I said it's not. Too much water. I drink like 5 of those, okay?
Not kidding.
Dude.
My mom's gonna be late because it's traffic out there. We're not gonna be here. Oh, this one is.
Ow. Ow. Oh my gosh. How many points did I get?
You did today, look at that. Hey, look, that's on the grid. Wait, where did Emma go?
She went home early,
Oh.
so you guys will have to get her info.
Yeah. Oh.
Yeah.
We should give you the slap next
week.
Yeah.
I can't eat candy after.
Madam?
Oh.
It's not your best friend.
Your bad friend.
Yeah.
Don't
Oh, you trying to rip me off.
Oh, that's fine. Don't rip me off.
There you go.
Yeah.
They're dancing all right. Yep.
Like I'm just checking what's in here.
Right, right. Jamming. So I replaced my little glass jar that broke with this cool giant apple.
Apple.
Yes, I have disco rats today. Great fun. All right, so as we get started here, this is a fun slideshow for me because this is the first one where I use AI image generator for pretty much all these images you're going to see, almost all of them. So it was actually like a ton of fun. So there's our dancing rat. Yeah. You are spying on you, basically.
Yes.
There you go. Out of the way. All right. Everybody in?
Maybe.
Almost.
I'm not here.
Okie doke. So we are now in unit 3. So here's where we get into our real physical science business, right? This is where it starts to get more physical sciencey. So we have done all of our contextual business at the beginning. All right. So yeah, there's a lot of AI here and it was really fun. Anybody know what a hallucination is with regards to AI? Yeah. Yeah. Well, yeah, that. No, it's when, so the AI image generator, it starts with static, right? And then it starts kind of like working out what you wrote and it makes images and then you tell it, you know, do that again, or can you add this or that? So you should have seen some of the hallucinations, rats with 2 tails, rats with like 1 weird eye, an extra arm. And so, so if these are cute, you'll really like the Newton's Laws rats because they're all in Renaissance clothes. So I had a really good time with it. So yeah. Anywho, all right. So lesson 5, moving on and into motion. And my dancing rats. Yep. These rats have names. There's a whole story here. All right. So Drew, Drew, shut the pantry. Thank you. All right, so let's get moving. So frame of reference is what we are starting with here. Yes, I did ask AI to put cute gray rat in a little red toy car, and it did. All right, so frame of reference. So here we go. To describe motion accurately and completely, we need Lucas. Frame of reference. Okay. So your frame of reference, you have a system of objects that are what with respect to one another? Bailey.
Not moving.
Yes. Okay. So you need a frame of reference, huh?
Kind of like a car ride.
Kind of like, okay, this is Frank. Y'all see Frank?
Oh, that is great. Okay. I didn't have any name on one.
Frank. All right. Frank's gonna be busy today, y'all will see. So, question number 1, how fast is Frank driving?
He's slow. He's not moving.
He scooted on by. Anybody want to guess?
1.25 meters.
That's just straight up a guess, right? Like you don't know because you don't have the information to know. So
Couple hundred.
how about this question? If you were this tiny little ant, would Frank appear to be driving slowly or quickly as he went by you? What do you think, Piper?
Very quickly.
Very quickly? What do you think, Drew? Slowly? Okay, now you guys have different answers. So Piper, why do you think quickly? Why do you think quickly? Don't know? Just guessing. Drew, why do you think slowly?
I watched Ant-Man.
Okay, describe Ant-Man.
So it says it's smaller, which means it takes longer for the car to pass by.
There you go. So think about the tire of the car, okay? Those little black wheels on his car, little plastic wheels were there on the little toy car. Okay, if you're an ant, that's a big wheel and it's gonna take longer to pass by you, right? So that's part of frame of reference is relative size. So we need to keep that in mind. Now, how about if you weren't the ant, but instead you were this big old elephant, then what you think, Xander?
Quickly.
Yeah, it's gonna go by really quickly. And you know, elephants tend to freak out when like rats and mice ride by their feet. So we're lucky he went by so quick that the giant elephant didn't sing. So keep that in mind. We're not really focusing on relative size with frame of reference, but it is something to consider because it does play into it. All right, so what is movement in relation to a frame of reference? All right, Colin, it's relative movement and relative motion. And really, when you think about it, everything's relative motion. So try this. All right, sitting in your chair or wherever you are, be super still, don't move. Now, are you moving?
Yeah. Yeah. Yeah.
Yeah? No? Well, you're Adam, but are you moving?
Yeah.
Yeah? You are?
I'm weaving. I'm moving.
So how fast are you moving?
Baby.
So you're moving all right. So you are moving, in fact, super duper fast. You're on Earth. So you're currently spinning around and rotating at about 1100. I'm going to use miles per hour because that makes more sense to you. It's more relative. And then you're also revolving around the sun and you're hurtling through space at about 67,000 miles per hour. So from your point of reference, sitting in this room, you appear still. But if you're, if using the surface of the Earth as your frame of reference, you're going to look still. But if you're using the whole solar system, you're clearly not. Yes.
You are so you can.
Yeah, I found that one. That one's already counted. Yep. All right. So see, it's fixed here. Yeah. So most of these texts come with like study guides. If you've been with me before, you've seen like the worksheets that go with them. This one didn't have that available to me at any kind of, reasonable cost. So I had to type up outlines for every single chapter. So that's why there's more. That's why there's more typos in this class. Yep.
Different from the past
Yep.
years.
I had to do them all. So, yep. All right. So still thinking of frame of reference here. Is Frank moving? All right. Now watch.
Yeah.
Oh, did you see him? He went by real fast. Let's try him again.
Appeared out of existence.
Is Frank moving? Let's see. Think about it. Here he comes. He's moving. All right. You think he's moving?
No.
All right. Now hold up. Now I love it. Everybody doesn't agree. So how about, is it Henrietta that's moving? Well, who's Henrietta? All right. Well, you're about to meet her. Okay. Who's moving? Frank or Henrietta?
Oh,
Frank,
It looks like Frank's driving towards Henrietta, right? How do you know Henrietta's not moving towards Frank?
because your feet are still.
Because her face. So again, from Henrietta's perspective,
Right.
Frank's moving to her, right? But from Frank's perspective, like Henrietta's getting closer. as he gets closer. So frame of reference, perspective all plays in. All right, so
I thought it was backwards for a second.
yeah. So what do you choose? Your frame of reference has to be what? Caitlin?
Meaning.
Yeah, it's gonna be meaningful. It's going to be relative to what you're doing. So outside today, if you had included the rotation and revolution of Earth in your calculations, what does that mean in reference to what you're doing? It doesn't mean anything, right? So what you're doing needs to have meaning, okay? Now, what you got? Do you have something? Xander? No? Okay, so distance and displacement. So let's talk about this. These are different things. So how do we measure distance? I love AI's version of Frank and Henrietta's houses. These are great.
Doesn't have a car.
These are, well, I don't know. She likes to walk. She's very health conscious. All right, so look here. What is the length of a path between 2 points, Yusuf?
Yeah, how distance?
Distance. Yep. Okay. Your distance is your length of a path between 2 points. And everybody knows this one, so let's say it together. Shortest distance between 2 points is a
Straight line.
straight line. Heard it your whole life, right? Okay, that better be the case. So if he's going to move here, we have to decide what units are best suited. All right. So if you're measuring long distance, you're going to want kilometers, shorter meters, and centimeters if you're moving very small distances. Now, when we get to adding in our time frame, you may want to use hours, seconds, minutes, days. Think about it. We talked about how many Earth days is a Venus day, right? It matters what you're using. It has to be meaningful.
That picture of Frank is the size of a one-story building.
Yeah. Frank and Henrietta, they're not quite in proportion, or the houses are far off. This could be perspective.
It's all about frame of reference.
Yes.
Wait, maybe the house is gonna fall on his head.
So here's your formula. All right. Now, who wants to take a stab at reading it in words? How would we read this? Ooh, Bailey.
Delta X
Mhm.
equal to. That's all I got.
Okay. All right. It was a good try. All right. Colin.
Delta,
That's a delta.
delta X equals X sub F minus X sub I.
You could read it that way. But if X represents position,
That's what I'll-
then what do we think this could be? Yusuf, you want to give it a shot?
Change of X equals X plus F minus X.
Okay, we added a word here. Now we're in change. That's good. So the change in, put the word position in here for X and imagine, try to figure out what is F and what is I. Do you want to give it a stab, Jordan? You got change in, X is going to be what?
X is going to,
Position. So change in,
so X is position.
right. So change in position.
The change position is the XF minus
Mhm.
XI.
Yeah. What's XF and FI? Anybody want to guess? Do you want to guess, Asher?
F is acceleration.
No.
and I
Good guess, still. All right, let me do it this way. Say I wanted to walk from here to Milo. All right, and I measured it and it's 15 feet. If this is 0 and that's 15, Drew, do you want to take a stab?
Velocity.
Not velocity, so I'm going to help you out. It's going to read like this. Change in position equals final position minus initial position. So your I and your F are final initial. All right.
I was thinking before.
So it wouldn't make sense for me to go 0 minus 15, right? If I want to go to Milo and it's 15, so it's 15, which is final, minus initial, which would be in this case 0, so it's 15 feet. But if Bailey wanted to go, she's like 6 feet closer. So it would be 15 minus 6 is where she started, initial. Okay, so we're going to look at it in a minute. You'll see it. So sometimes you'll need to convert units in your equations. So when converting units, centimeters to meters, years to days, you need to use what? Do we know?
Conversions.
Who's got it? Do you have it?
Great.
Xander?
Conversion factor?
Yeah. Okay, you got it. So we're looking for conversion factors. Xander got it. All right. Has everybody done fractions to some extent?
Yeah.
Okay, if you've done fractions to some extent, this won't be as hard as it seems, all right? This is where the mathy gets in, but it'll make sense. So you set up an equation with fractions in which the numerator or the denominator of your conversion factor cancels the numerator or the denominator in the fraction containing the information you already know. Blah, 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 mathy, mathy. Okay, so if you want to know how many centimeters are in 3.12 meters, I bet some of you can look at this and just tell me. Like, what would you say, Jordan? What would you say?
Oh,
How many centimeters are in 312 meters? 3.12 meters. Do you want to take a,
Sorry.
Yusuf? That's okay. Yusuf, you want to take a stab at it?
well,
312. Okay. And what did you do? Oh, I'm sorry. What were you going to say?
I had a brownie point,
Oh, okay. Which one?
in the binder.
Yeah.
It says if a lost dog turns up 5 miles from home.
Yeah.
Displacement is 5 miles.
Right.
It doesn't describe the distance you actually traveled or wandering about.
Yeah. We'll get, yeah. Well, wandering about. Just wandering about. Yep. We'll get there in a second. So, all right, Yusuf, what did you do when you got 312 centimeters? Like, what in your head, what did you do?
I just changed the decimal point.
Right, you probably just moved that decimal point 2 places to the right because you know that's how it works, right?
And then
Centimeters.
centimeters to the meter.
So that's what you did. But what you're really doing is actually some more complex fractions than that little just scooching a decimal bit. And it's important that you learn to set it up the right way because there will be times as we get more involved in this class, and definitely in chemistry, where you have to put your conversion factors in so that you can cancel units. So here's what I mean. So in this case, your conversion factor is going to be 1 meter is 100 centimeters or 0.01 meter is 100 centimeters. And what are we trying to find? We're trying to find centimeters. So what we're going to do is we'll set it up as X centimeters. We don't know how many centimeters, some kind of centimeters, right? Question mark X is 3.12 meters. So this is the one we want to use because what we're trying to do is get centimeters on the top and get rid of meters. So the way to get rid of meters is to put meters on bottom. So you want 100 centimeters over 1 meter. That's basically the same thing, right? 100 centimeters is a meter. So that's 1, really. So you're all you're going to do here is multiply by 1, but you're going to cancel out the meters. So we're using unit cancellation, okay? Why that moved. So then you're going to do, once you got rid of the meters, that was easy. You're just going to multiply by 100, which is what you did in your head to begin with, and you get 312, right? All right. What are you giggling at? Y'all are funny. All right.
Oh,
So measuring displacement. Oh no, Henrietta has lost Fido. This is Fido, y'all. Uh-huh.
on the previous slide, it's
Fido?
not cancel with 2 L.
Oh, did it? Because it's
Each.
cancel. Yeah, okay.
Is that Fido up top?
This is Fido. Okay. And this is Henrietta's pet. See, she's got the leash, but she's lost him. All right. So here's where our story begins. Okay. So here's where our story begins. So got to kind of follow along. So be paying attention and be watching. All righty. Okay. So this is where Henrietta and Frank live. Now, AI was good enough to give me all these houses, but it was really not great at giving me this nice little chopped up city neighborhood block. So I had to manually do that. So it's got some like kind of weird stuff, artifacts in it. So no worries. But basically one of these blocks is a meter. Okay. Let's just pretend it's a meter. It's a meter because it's rat land, so it's small. All right. All right. So this is Henrietta's house, right? Okay. And so Fido he ran off. She's lost him. So now she's got to figure out where the heck he went. All right. Lost him. All right. So we got to help her. All right. So here comes Frank. He's going to come to the rescue because she needs Frank to help her find Fido because he's got a car. Plus he's her buddy. So he's going to come over here and he's going to help her. All right. So how far did you travel to get to her house?
5 meters.
Look close.
Wait, 4.
He went 4 meters. Okay. So it's 4 meters from Frank's house to Henrietta's house. All righty. So good. They're there. But Fido isn't there. So they got to go get Fido.
Oh, no.
All right. So how are we going to get Fido? So they're going to get out of the car and they're going to go on foot because they figure that's a smart thing to do. So they're going to go walking and they're going to try and find Fido. So they walked 1 meter, 2 meters. They got to turn. Got to disappear for a second when they turn. Now they're going to go up here. Okay. 2 more meters. So they went right here. If you look right here, you see a compass. So they went 2 meters westbound and 2 meters northbound, which means they went 4 meters, right? They went 4 meters and they found Fido. Thank goodness. Don't they look happy? Hooray. All right.
Frank's in his car.
I don't know why he's still down there. Ignore him. He's not supposed to be there. I'll fix him later. So This was complex. We're talking like hours and hours of slide animation. All right.
Tries to figure it out.
So that was distance, right? They had to travel 4 meters to get to him. That was their distance. So what's displacement? So distance is your path between 2 points. Bleh. And Yusuf, what were you gonna say? No. Okay, Xander.
I found brownie point.
Hmm.
It says C measuring displacements, and then it says D net measuring displacements again.
Yeah, I told you guys there are gonna be some of those formatting things. I'm not worrying about the formatting. That's just auto formatting. That's craziness. Yes.
It also says
Mm.
on the bottom it says quantity has.
Yeah. Like, do you have it or have you had it? What, I don't know what sentence you're in, so we'll get there. All right. So distance is your length between 2 points. Your displacement is your direction from the starting point and your length of the straight line from starting point to ending point. So you're thinking kind of as the crow flies. So this is where you were kind of lost, Jordan. So if a pet turns up 5 miles from home, his displacement is 5 miles in a certain direction. But that doesn't describe the distance he actually traveled while he's wandering about. So if Fido's up here and that's his displacement, he could have wandered all through those little piles of corn to get there, right? Okay, so yeah.
What was all the corn for?
Well, we're gonna assume that he kind of meandered his way through it to get there. Like he may have gone through all that is my point. Okay. So displacement is an example of a vector. So I'll give you the first one. A vector, y'all should know this one if you've watched a certain movie, has to, it filled itself, direction and magnitude. So if you can always
Oh,
this one you should know, right? Anybody not seen Despicable Me? Because that should be an assignment if you haven't. Okay. Oh yeah. So I love that. I could watch that all day. It was great.
Just watch it. It's
great.
It's not a role model. maybe.
Mm-mm. So a vector has direction and magnitude. So magnitude can be size, length, amount, and you can add displacements using vector addition. Yes.
Yeah, this is what it says in the bottom. It says vector quantity have vectors quantity have has magnitude and direction.
Okay. All right. So
You can see it if you want.
I believe you.
Also,
Okay. Yeah.
Instead of B, it does have a weird question mark.
Yeah, I told you guys there were going to be some formatting things. And in this lesson in particular, you guys were missing some specific graphs. Like I mentioned that last week. There's some specific graphs you're missing that wouldn't make sense. Just get to class and you'll see them. Okay. All right. Brownie points are awesome, but if we distract from the lesson too much, we're going to be in a bad way. All right. So, all right. How do we measure it? Yes.
Future classes on this, you should like replace the vector with like a rat.
Okay. So how do we measure displacement? All right. So we can measure on a straight line. This is the easy way. Here's a little line. See, ta-da, and there's Fido. All right. So when two displacements represented by two vectors have the same direction, you can do what, Bailey? You can add their magnitudes. In this case, the magnitude is length, okay? So there's going to be a couple random beeps. That's just those stopwatches. Just ignore them, okay? Now, let's see. Vectors can be labeled as a letter with an arrow on top, okay? If you've done algebra or geometry, it might be like you good there, Lamb? It might be like a ray. Oh, stop it. So, alrighty, let's see here. So we're going to solve for A. Okay, this is going to be vector A. So what do we do here? Here's our, there's our formula and Fido just shifted. So the change in position equals the final position minus initial position. This is the magnitude of vector A. So in this case, our final was, we went from, initial position. Did I write that wrong? Oh, I should have written it backwards. I wrote that backwards, but anyway, it should say 3 minus 1. Anyway, so just final minus initial. I just typed it wrong. So it's 2 units to the right. Okay. So if we're going to solve for B, all right. So again, there he goes. So now we're wanting to do our final minus our initial. Our final was 6. He started at 3. That was our initial. He moved 3. So we can add these together because they were in the same direction. So basically your change of 2 plus a change of 3 is a change of 5, right? Duh. So in this case, he moves 5 units to the right. with displacement, you have to have a direction. You can't just say he is 5 units. 5 units to the right. We don't know what these units are, do we? Centimeters, meters, miles, kilometers. I don't know. It's a unit. It doesn't matter. All right. So when diagramming vectors, you show magnitude by the size of the arrow. So if you got a little arrow like that, that's 1, then a bigger arrow is 2. Right? Okay. So now what do we do if we're on a straight line, but the displacements are in opposite directions, Xander? Yeah, they're going to subtract. Very good. So they're going to subtract from each other. So it basically is adding a negative number. So here's how it looks. So if we're going to solve for A, again, vector A in this case. So here he goes. Whoa, okay. Our final is 7. Our initial is 1. That's how many? A change of what? 6 units. Okay. Change 6 units to the right.
This is just like distance between 2 points.
Mhm.
and the graph and-
Right? That's basically just distance, but this is why it's displacement. So if we get to B here, and oh, now it goes the other way. Okay, so now we have to say our final was, oh, I wrote that one back. No, I didn't. No, I didn't. So final was 3, initial was 7. So what number do you get with 3 minus 7? Piper? Oh, you got, yeah. -4. So that is to the left, right? He went to the right, then he went to the left. So now you're going to add these together because that's our formula. We're going to find out what our total displacement is. So it's a change of 6 and a change of -4 equals a change of 2. And he started at 1, right? So he went 1, 2. So that doesn't say how far he traveled, does it? It just says how far he was from where he started. So he's 2 units to the right of where he started. All right, so that's a straight line, but what if it's not straight? Do you remember Fido? He kind of went down the street and then turned the block and went the other way. Okay, so how do we find the displacement? Here's what we do. All right, you got to make a straight line. So we're going to keep these simple. We're not going to get crazy physics. We're going to keep simple physics. All right, so graphing is often used. And do you know the answer to this one, Jordan? The vector resultant vector is going to be your sum of 2 or more vectors. So how do we create a straight line we can measure? Lucas, did you?
What tempted him to leave the house?
Corn. Yes.
You draw a straight line from where you stayed.
Okay, you saw something. All right, so what do we do here? We got to make a straight line. So how do we find this answer? Oh, here we go. We're going to use geometry. Anybody done geometry yet? Okay. This is going to look really familiar. So when you're doing these math problems and you're like, there is no practical application for this, I don't understand where you'd ever use this. Here's where you use this.
And another.
Physics and another.
Well, so here we go. Let's make the neighborhood a little lighter so we can really see the blocks. So remember our unit here, we got a meter for these little squares, these little blocks. So he went this is his displacement. He's this far from home. But what is that? So we're going to use Pythagorean theorem. Let's all say it together. What is Pythagorean theorem? Yes, a squared plus b squared equals c squared, where a and b are the legs and c is your hypotenuse. So in this case, we want to solve for that hypotenuse because this is the hypotenuse and this is his displacement. Oh, look, it's geometry. It's for real geometry. So how's this work out? So here's what we do. We want c, right? This is our hypotenuse. Alrighty, so in order to get c, do we want the answer for c squared? Okay, we want the answer for c. So, all right. What does it mean to square a number?
Multiply by itself.
Jordan,
Yeah.
multiply it by itself. What does it mean to take the square root of a number? Yusuf.
Let's cut it in half.
Yeah.
Kinda, yeah. It's like, what is it?
People.
Can you describe it?
It's like squaring is opposite, so you divide a number by itself.
Yeah, dividing it by itself is really what it is.
Mine is a square root of 8.
Okay, hold on. Oh, okay. Smarty Pants over here is jumping to it. All right, so Mr. I hate geometry and giving me a hard time about it. He's over there doing it. All right, so here's how we do it. So this is what we're trying to find. So how do we do this? We're gonna take our measurements, 2 meters squared, 2 meters squared. What's 2 squared? 4. So now you got 4 plus 4, which is what? 8. So now we're gonna take this. We're gonna come up with our square root of 8. Now, don't try and do this by yourself. If you want to do this in math class by yourself, knock yourself out. If you think it's fun, knock yourself out. Otherwise, just either put it in your graphing calculator or ask a digital assistant. Alex could probably do it in his head. Ask Alexa, ask Siri. They'll give you the answer, right?
Simplify it to like it's 2 times the.
Yeah, you could do that. But in this case, like I really want to know how many meters he was from home. So he was about 2.8 meters from home. All right, so let's try another example. So today, after sitting in here in class, learning about displacement and distance, you get a hankering for a chicken sandwich. Who doesn't, right? So you open up Waze on your phone. Who uses Waze? I love Waze. So you're going to type in Chick-fil-A. The reason Waze is the advantage of Waze over like Apple Maps or what are those? It's social data. So people enter information. Like, I don't know if anybody you use it or used to using it, but not only does it give you a route and traffic and tell you how to get around traffic, which most GPS routing will do, Waze has for people who are driving to be like, oh, there's debris in the road. There's a cop over here, you know, stuff like that. So Waze combines social media with GPS mapping. So it's really kind of unique and it's cool that way. I love it. So you want to go Chick-fil-A from here. All right. So when you type that in, this is what you will see. Okay. You're going to get this result because the closest Chick-fil-A is right over the river over here. Okay. It's 2.7 miles. Question?
It says in the phone 9:10. Should that be a value point?
I can't change what's on the phone, honey. That's what time it was when I did the screen capture. All right. So, all righty. It's 2.7 miles away. You're excited about this. That's not too far. All right. You could walk that if you wanted to. You could do it on your bike. All right. But there's a problem because there's a river in the way. So you're going to hit, view routes and tell the phone to route. Okay. And when you tell Waze to route, you click that little button there. It's then going to tell you it's really 5.8 miles because the displacement of Chick-fil-A is 2.7 miles, but the distance is 5.8 because you can't drive through these houses nor over the river. That would not be fun, right? So there's there's a real life distance displacement that if you're driving, I can't tell you how many times I've put something in and been real excited about it and been like, oh, it's only right around the corner. It's really not. Yeah.
That happened to us once.
Yep.
To a friend's house, and said, well, I was like 5.8 miles. Like, wow, it's only 5.8 miles, but one asked me for those like 10 miles away.
Mm-hmm.
I mean, I can relate to party.
Which is typically going to be longer, your displacement or your distance in most cases like this. Yes, Xander. Yeah, your distance is typically going to be longer because you gotta make your way around things usually. All right. So although it's only 2.7 miles displaced from your location, it's a 5.8 mile distance. Bleh, that kind of ruins stuff. You don't want that, man. You want to get there fast. So if it closes in 50 minutes, then you better get a move on. So locating and rescuing Fido caused Frank and Henrietta to work up an appetite. So they both have a hankering for a chicken sandwich. So Frank opens his phone, goes through that whole thing.
Hankering.
A hankering. I mean, you're jonesing. You want it. So speed and velocity. So what is this? All right. Now, this will help you. We just talked about those little triangles. We're going to talk about it again. So yeah, Fido driving by. So speed's a ratio. And mathematically, a ratio is what? What would you say? Mathematically, what's a ratio?
Like the compared to the two things.
Mm-hmm.
That's-
Yeah. What else would you say? How else would you describe it?
Where it's distance of that an object moves,
Mhm.
amount of time.
Right. Distance
Like
to time. So you got that right. So if you saw my shirt earlier, you see my shirt? Distance raptor over time raptor equals velociraptor. Can you remember that now? Yeah. I get to wear nerdy shirts. It's cool. when you teach science, you have an excuse for all the nerdy clothes, and it's really fun. I would wear it even if I didn't have the excuse, but hey. All right, so.
I saw on campus,
Uh-huh.
someone had the evolution shirt.
Oh,
And it had like the three, like the water, fire, earth.
Yeah,
seeds, and
that's
it
funny.
was adorable.
That's
I
cute.
forgot.
So my favorite clothes people have all the nerdy dresses and stuff. They just came out with one yesterday that was science moles. So if you've done science and chem with
Oh,
me,
No, I don't
you've done moles, and it was little moles and beakers. It was great. I'm gonna buy it. I'm gonna buy it. So speed is distance over time. You can also say velocity is distance over time, and that can be meters per second, kilometers per hour. And this little slash is read as a per, which makes this a fraction, right? It's a fraction. This ratio is a fraction. Okay. So here's Henrietta. All right, now, what kind of speed is computed for the entire duration of a trip? Jordan?
Speed.
No, wait, let him answer. Average speed. You are right. Okay. And then what do you call it at just an instant, Lucas?
It's instantaneous.
Instantaneous.
I'll find a brownie point.
Okay, what is it?
Says instantaneous speed is measured at a particular instant.
That's correct. Instantaneous speed is measured. Oh, we're gonna go with that. All right, fine. It's up here too. All right, so there's also constant velocity. So this means both a constant speed and a constant direction. Constant direction is a straight line. So constant velocity means motion in a straight line at a constant speed. So if either the speed or the direction or both changes, then the velocity is changing. All right, so what does this mean? How do we do this? So, all right, your average speed, there's a formula, right? Okay, let's say that's 3 centimeters and that's 2 centimeters. All right, Fido's gonna do his thing now. Fido is going to start moving here,
Crash.
and he's driving. Now, we can time him, right? We can time Fido.
Crash.
That was 8 seconds. All right, here he goes. She's kind of worried because he's going real fast. That was 5 seconds.
That
That was 3 seconds.
She was so worried.
When you ask AI to make a cute, white, photorealistic rat look shocked, it comes up with some very interesting things. So there she is. Now we have these speeds. These are our 3 different speeds. What's our distance? Who knows what we're working with? Bailey? Piper, I'm sorry. Piper's hand went up.
10 centimeters.
10 centimeters is spot on. All right, we're dealing with 10 centimeters. All right, because it's 2 plus 3 plus 2 plus 3, 6 plus 4 is 10. And 10 centimeters. All right, so now we can take this and we can say if you went 10 centimeters in 8 seconds, you do the math, it's 1.25 centimeters per second. If we say, what was the one for 5? Do that, 2 centimeters per second. And if we want to know the one for 3, what do we get? 3.333333333 centimeters per second. So that is our speed.
These until the end of time.
Yep. So again, so what do you want to find? This is where your little triangles come in handy. If you look, okay, if you look on the back, hold up. Oops. If you look on the back of your binder, you'll find a bunch of triangles. Okay, now everybody has their binder with them so you can see them. There is a use for every one of those. So make sure you understand how to use them. How to use them is that D is on top. So if you want to find the D, the 2 things on bottom are side by side. When you have 2 factors side by side, it means you multiply them. So you want to find distance. You find the distance. All right. And if you want to find speed, what do you do? Speed's the S. Sometimes you'll see that as a V.
Divide distance by time.
Right. And if you want to find time, what do you do?
Is speed.
Divide distance by time.
Distance by speed. Okay. Sometimes you're going to see the D. S. I'm sorry. You can see S as V. Sometimes it'll be written as V for velocity. Sometimes it's written as S for speed. Same thing, right? No worries about it. So all that always works out. You can use these little triangles, great, because you can flippy flop math around as long as you're following rules, right? So slope of a line on a distance time graph is the speed. And a typical graph is going to have your horizontal X, Y axis. You've seen this, right?
Yeah.
You got your horizontal X, your vertical Y. How do you remember that the Y is the vertical one? Anybody have a trick, Yusuf? You just remember? Well, that doesn't help. Who's got a trick? Anybody know the trick? Do you know it?
So like the X is like.
She's trying to explain her own tricks in her head. Yeah, yeah.
I just remembered that like. The Y is, to me, like the Y, you can drop.
Yes. Okay, she's got it. So
Compared to,
that
like, the X.
this font's a bit off, but if you imagine a perfectly typical Y, it's like this shape, right? And it just keeps going down. So James is doing a Y. So if you imagine that the bottom of the Y, the stem of the Y is just going up and down, you know that Y is always going to be that axis. It's the vertical one. The horizontal one, it'll smack into that letter and cross it. So there's your X.
Or since it's in the ground, it's X marks the spot.
Okay, that's a good one too. All right, so now what do we do? So your horizontal X, when you do these graphs, what is the X typically? Jordan,
X.
what's it represent typically? Not sure? Yusuf? No? All right, so typically our X is our time. Now, could you do it the other way? Yeah, but visually this is much better and you'll see why. So if the X is time, then what's the Y? Asher?
Distance.
Ah, there you go. All right, let's see. I'm looking to see who hasn't answered yet. I know who you are. We've got 3 of you. All right, so that's going to be your distance or position. You can see that as written either way, okay? So the slope of the line on a distance time graph is the speed, and plotting the instantaneous speeds at 2 successive, one following another point, allows for the graph of the slope, which is what you're doing with your lab, right? You're doing this exact thing. So I'll give you that. I just pretty much there. The slope of the line represents the steepness, right? Or your slant. And a slope on a distance time graph demonstrates your rate of change. So what's that mean? So this line shows a great change in position in a small amount of time. Do we know what our unit of time is here? It says seconds, so we do. But could it be anything? Yeah, it could be anything. And then that position says meters. But you know what we don't know? It says seconds and meters, but it doesn't say whether each of these little lines is 0, 0, 1, 2, 3, or is it 5, 10, 15?
That's how graphs can be manipulated to look more extreme or less.
Yes, very good point. So you really want it to the scale to be the same. But in this case, you've got, you know, let's just say that it doesn't matter what these units are. You can tell that he only went what, 2 units of time, and however many, I think that's 20 position change. Okay. So this one though would show a small change in position during a great amount of time. So to calculate a slope of a line, let's see, geometry people, let's say it all together. What do you calculate?
Rise over.
Yeah, rise over run, algebra people, really. So rise over run. Okay, rise over run, which is position or distance over time. Where have we heard that before? Distance over time is? Distance raptor over time raptor. Yes, there you go. All right. So you see how that makes sense? You can see the speed on a graph. You can visualize the speed. So graphing motion, we just went over this. This is just a little couple images, refresher. That's not a triangle. That's your delta, right? 4th letter Greek alphabet. Alpha, beta, gamma, delta, epsilon, keeps going, blah, 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 right?
Hi.
That's somewhere down the line. So you do your rise over your run, which is your change in position over your change in time, and you get basically your speed or your velocity. So it shows different slopes, can be calculated in segments. If you want to, like Bailey was pointing out, you want to make sure that you're not manipulating it so it looks weird. Some people will do that. All right, so this is the part that was missing in your lab. So Chester Cheetah is chilling under a tree. This was really challenging for AI, let me tell you. All right, so, we had some weird eyeballs on these cheetahs. All right, so
Cheetos.
this is an object at rest. Here's his position, not moving, is he? It could also be flat along the bottom, but we're gonna, maybe we've marked a starting point as 3 units away from wherever, okay? So he's at rest. All right, now he spies an antelope, gets up, starts to chase. So you can see here, he's excited. Oh, look at him. Can you see? So he's very excited. All right, so he's like, "Woo, lunch, right? All right, so you can see how he's moving forward, right? So this is when he's steady running. When he's steady running, you see this nice increase. Oh, yeah. Now this next one's great. Let me just tell you, if you want to see hallucinations, try this cheetah catching an antelope business, because this antelope had like 8 legs, eyeball in the wrong place. Took me a while to get a decent one. So he has to slow down so that he can bite. You can see that this speed, see how it was nice and straight before? He was going really fast, and now he's slowing down, right? And he's got to slow down so he doesn't run past it.
You just know what?
So now, depending on, guys,
5 legs.
Chest is moving. That chest
So-
is missing a leg.
yeah, well, no, it's behind him. So, depending upon where you set up your final point, like some of you guys had your final point right in front of the garage door. Bailey's team did. So if your final point was right in front of the garage door, you might notice that when you start looking at your graphs, that maybe people slowed down a little bit before that last step.
It wasn't like right.
Yeah, it wasn't right there, so they couldn't have taken a step.
Foot and two.
But you may watch some people might slow down. And if you graph the Aussie one, you might notice he probably slowed. Yeah, he was fast. He may have slowed down a little at the end too, so that he wouldn't just like slam into us, because he was hauling, right? I mean, he was hauling.
Well, it was hilarious if we did.
So we're gonna play a game. Let's guess that action. We're gonna take votes by a raise of hand. Okay. All right. So
Let's go.
what we want to know here is, what is Frank doing? Is he taking off in a plane, chasing Fido and catching him, walking to and from the mailbox, or beginning a road trip?
Well,
So if we think he's taking off in a plane, raise your hand.
Wait, 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 wait.
If you think he's chasing and catching Fido, raise your hand. If you think he's walking to and from the mailbox, raise your hand. And if you think he is beginning a road trip. Okay, so in this case, he's chasing and catching Fido. So he's running here. You can see he's moving at, he's kind of still, but he's kind of still right here, but he had to get him. Like, this is right at the end. This is that catching. Yeah.
Slowly started. to
You got to slow down. Right. All right. So how about this one? What? Yeah. Oops. No, didn't say it. All right. Fat fingers. So he's walking to and from. How can you tell? By looking at that graph, not by guessing my answer. Yeah. Wait a minute, Bailey. Yeah.
because it went up, it stayed, and then it went
Mhm. So right here, what's he doing right here?
probably get in the mail.
Getting the mail. Standing there looking through it, going junk, junk. Oh, that's a bill. Darn it. Junk. Right. That's what he's doing.
Magazine subscription.
He's walking to and from the mailbox. All right. Now, what's he doing here? We got 2 left. We got taking off in a plane and beginning a road trip. So you're really going to want to pay attention to your time and your distance. So what do we think here? How many think he's taking off in a plane? All right. How many think he's taking a road trip? All right. So he's going to be taking off in a plane because he went, what, 55 meters in, oh no, wait, I'm sorry, 100 meters in 50 seconds. He was moving. All right. So that's taking off in a plane. So this last one is obviously beginning the road trip. See where he he probably was exceeding the speed limit a little and thought, oh, I better slow down so I'll get tagged, right? On his road trip, moving along. Yeah, you don't want that. So
Chester's not young as a police officer.
when you put all these overlapping, you can see, shh, God, watch the side chat. So you can tell by looking at a graph kind of what the action is. This is why graphing is cool, because now it gives you a visual representation of the motion. Liam?
Chasing and catching Fido is different.
Yeah, I flipped it one way and then I accidentally flipped it back. And really this isn't so much chasing. This would be like, well, is it this one? No, which one was it? Oh, it's different here. Yeah, this one's correct. I think the other one was wrong. Chasing, running the same. It should have had a dip right there and it didn't bend. So anyway, but you're right. You called out.
Whoa,
All right, so
that's Jim.
hold up here. So velocity is
Yeah.
what and what in which an object is moving, Colin?
Direction and magnitude.
It is the direction and magnitude or speed and distance, right? Which in this case, distance, this is going to be your distance is length. It can be anything.
The binder says velocity, speed, and direction.
Yeah, or speed in,
The direction.
Distance.
oh, that's okay. So that's here. So yeah, there you go. All right. This, by the way, was one of the hardest things to get it to do, but I really liked him.
Rat in a jumpsuit.
He's cute. So we're gonna watch a quick video on adding vectors. Yeah, gotta do some mathy math. Come on, do your thing. I'm clicking you. Oh, shoot. What are you doing? No, no.
Now you know.
Go. Oh, my.
You know, I think this is a sign from God to just skip this part.
No, you don't want to go.
Okay, we'll stop.
I can do it this way, though. Hang on. Oh, look at this. It's all funkified for me. Hold up. Mhm. Hold up. I'm gonna fix it.
Oh, yeah.
We just go here.
Oh, the thing behind me.
I can't touch coins in my hand.
Body point.
No. Now, y'all don't be texting yet. Hold on just a second. We're gonna do this first, and we still have classes and over till 1:30. So, what's this? Oops.
I'm gonna add two blue kids.
No, let me just go straight to YouTube. Hold on, I'm gonna find it. I don't know why it doesn't want to go. Give me trouble. Let's try it again. Hang on. Oh, stop.
Ow.
Da-da-da-da-dum. This doesn't work. Last but least, I know. Oh yeah, he's great, isn't he? I seriously could watch that little GIF all day. Where's the one I picked? We could always do Professor Dave, but no. Okay, Professor Dave is the best, but let's do it this way. I want to make sure that you're seeing the same one. So this is where you guys know that these are in Dropbox. I think I've put it in already. Let me double check. But it should be there. If not, we'll give up and we'll pick Professor Dave. Ba-ba-bum. Yeah. Did somebody call me? No? Oh, somebody said my name. Ba-ba-ba-do-do-do-do. All right, y'all are good. Oh, okay. Not sure if I put it in this list yet or not. If not, that's fine. We'll just do Professor Dave. Here we go. Nope, it's not there yet. All right, so we will go over here and look at our friend Professor Dave, because I don't think I picked the other one because it was shorter, but oh wait, there's the one. There it is. Okay. You can watch Professor Dave too if you really want. We'll watch that after this one, but let's do so. We're probably gonna get a commercial because it's not embedded in the slideshow, but that's all right. Sometime today. Here we are.
It's 15 seconds.
No, Lululemon, I could care less. Why do you mark it to me? All right, get your volume.
Another word for size and direction. To show their magnitude and direction, we draw vectors as arrows, because arrows also can have a size and a direction. To draw a vector, just draw an arrow pointing in the vector's direction and then write the magnitude of the vector above it. So as an example, if I want to draw a vector, I need to give it a direction and a magnitude. So I'm going to give that arrow a certain size and then label its magnitude above the arrow like this. So this vector literally means 10 meters to the right. These are a few more examples of vectors with specific labels. The arrow's length depends on the magnitude. The bigger the magnitude, the bigger the arrow. And if you double the size of the magnitude, you double the size of the vector as well. So if this
What?
is 10
There we go.
meters and we want to draw a 20-meter vector, we need to draw an arrow that's exactly twice as big as that original arrow. The reason why we proportion them this way is that this helps us see the relationship between multiple vectors. Example, if you're trying to just describe motion.
Good. Hang on, let me pause so we can buffer a minute. By the way, does anybody know where this is? It says DuPont Circle,
Washington.
Washington DC. That's where DuPont Circle is. All right, man, you buffered. Let's play.
Having the sizes of the arrows representing the actual sizes of the arrows can help you visualize motion much more easily than if they were just arbitrary sizes like that. So you get a clearer idea of what's going on. The symbol we use for labeling vectors is a letter with an arrow above it, so that's a variable, that's a stand-in for a vector. So this is vector A. Vector A is equal to 10 meters to the right. And it's totally arbitrary which letter we use for which vector, as long as we're using a letter with an arrow above it. That's a variable that stands in for a vector. The same letter without an arrow above it means the scalar magnitude of that vector. So if I just drew E without an arrow above it, and E with an arrow above it means 10 meters to the right, E by itself just means 10 meters. So that's a notation that we use. So I can see these are all vector quantities, and if I wanted to represent them as scalars, this is how I would do that. Pretty straightforward.
Pretty straightforward.
If you multiply a positive scalar by a vector, multiply the scalar by the magnitude of the vector and keep the direction the same. So as an example, if I multiply this by 2, that means I'm multiplying the magnitude by 2, but I'm keeping the direction the same. So 2 times vector A is equal to 20 meters because it's 2 times the magnitude, and the direction is the same, but the vector is now twice as long. If I multiply the vector by 1/2, this is what it would look like. Pretty straightforward. If you multiply a negative scalar by a vector, multiply the scalar by the magnitude of the vector and flip the vector to face in the opposite direction. So multiplying by a negative number flips the direction of the vector to aim in the opposite direction. So negative 2 times A would be 20 meters to the left here. Now we're in the part of the video about adding vectors. There are rules that make adding vectors different than adding regular numbers because vectors also include direction. So the directions of the vectors you're adding are going to matter for their sum. So the first step to adding vectors is to connect the tip of one vector to the tail of the other. The tip of the vector is the point of the vector right here, the very front of the arrow. And the tail of the vector is the opposite end of the vector right here. So just remember the point is the tip and the opposite end is the tail. So we're going to connect the tip of one vector to the tail of the other, and it does not matter which order we do this in. I'll talk about that more later, but what matters is that the tip of one is connected to the tail of the other. So if you watch up here, you can see these 2 ways of connecting the tip and tail are correct, and these 2 are incorrect. The connections on the right are incorrect and not how you use the tip to tail method. So step number 2 is to draw a vector that begins with a tail at the tail of the first vector and ends with a tip at the tip of the second vector or the last vector that you're adding. So if I draw that for these 2 vectors, the 4 and the 3, I get a new vector that looks like this. So it starts at the tail of the first and ends at the tip of the last like that. So an incorrect way of doing this would be to draw it like this. For some reason, a lot of students do this their first time adding vectors. So please make sure that you're drawing from the tail of the first to the tip of the last. This one's going in the wrong direction. Step number 3 is to find the magnitude of the new vector using the magnitudes of the original vectors and geometry. In this case,
Geometry.
specifically, I can see that these vectors are forming a right triangle. And I remember from math class that if I'm missing the side of a right triangle, I can use the Pythagorean theorem, a squared plus b squared equals c squared. So plugging in my numbers here gets me a final vector value of 5. We're going to be using the Pythagorean theorem a lot in this class because vectors that form right triangles come up a lot. We'll learn how to deal with more complicated shapes later. The main thing I want
No, we
you to
won't.
know for now is that you'll have to use geometry to figure out the length of the missing vector in addition to the other 2 steps. This is it. The answer. What the aim at the
Yep, hold on. Buffer. All right.
sum is equal to this new vector of 5 pointing in that very specific direction. The direction of the sum matters a lot. So when you're adding 2 vectors together, you have to consider both their size and their direction and use this 3-step process to find what that final vector looks like. Just to give you an intuition of why these vectors look the way that they do, why they add together in this way, we can imagine that you're running along a soccer field. And let's imagine to start off that you run at a certain speed along the field from one end of the field to the other. And then you run at a new speed across the field from one side of the field to the other like this. If someone were to tell you to run in both of those directions at the same time, to perform both of those motions at once, that would be like adding those two vectors together, adding those two motions together that you were performing. And if you add both of those vectors together, this is what it looks like. And so you can see that by adding those two vectors together, we get this new resultant vector, the blue vector, that's not just the numerical sum of the two. It's not just the regular old sum of the two. We have to use this tip to tail method to find that final value. So that's why we say that the sum is what it is for vectors. If we have two vectors pointing in the same direction, it's very easy. We just do the tip to tail method again, connect tip to tail, draw that new connecting vector from the beginning of the first to the end of the last. And using geometry, it's pretty obvious that this has a length of 11. If we have vectors pointing in opposite directions, again, we connect the tip of one to the tail of the other like this, so that 2 is kind of pushing back into the 6. And when I draw that new final vector from the tail of the first to the tip of the last, I can see that this is what it looks like. And so it's basically going to have a length of 6 minus 2, which is equal to 4. So that's how you find the size of vectors that are pointing along the same line. The order that we add regular numbers doesn't matter, and mathematicians have a word for this. They call this the commutative property. So no matter which order we add multiple numbers, it's always going to come out to be the same resultant number. In the same way, vectors actually also have the commutative property. The order that we add vectors does not matter. Any order will get the same result. So if I add these tip to tail, it doesn't matter if I do it like this or like this. Both ways, as long as they are tip to tail, yield the same final vector. We're going to do a quick check for understanding. You might want to pause the video here and just see if you can determine the size of each vector sum. I'm going to come back in just a minute and give you the answer.
Okay, so got paper and pencil? See what we can come up with. Y'all are like, no, really? Yeah, really. Do it. See what you can do.
Okay, well, the first one. Okay.
See if you can all agree on an answer. Actually, if you want to use the whiteboard over there as a group, we can open the whiteboard.
Yeah, it's more there.
Or I can do like, I can also do, I can also open a, and do it this way too. We'll do it like a whiteboard. Let me grab my stylus.
Whoa.
Yeah, there were calculators up there. Yeah.
Where is it?
So what was the first one? Let's look. Oh, man. 20 and 2. Let's say. Y'all are gonna tell me what to do. So we got two vectors going in this direction. What do we think this one's gonna be? What do you do with these? Okay, y'all know that one. You're gonna say straight up, we are 32, right? Okay, so let me write that down here. Make sure you guys, here, let's make it a fun one. Let's go. Ooh, rainbow glitter. Okay, so for the first one, we're gonna say 32, right? Make that thicker. All right, we're saying 32, right? Make it a little thicker for the people in the back. 32. All right. The second one was what?
4.
6 in one way and the other. We're saying 4. Now, you missed something with this. 32 what?
Units to the right.
To the right. Okay, so what's this one gonna be? 4 units up. All right, so let's come back over here. So this one's gonna be 32. We're going this direction, right? And what's the next one? 4 going up. All right. Now they get real fun. 10 and 20.
It's 24.5.
Oh, okay. Let's see.
4.9.
We got 10 one way. Okay, right? We had 10 going. Which way was 10 going?
Right.
That way for you.
To the right,
It's an upside down triangle, so.
right? And then we had 20 going. Which way?
Yeah.
Down. Okay.
10 squared is 100, 20 squared is 400. Then what was it? 400 600. The 600's
Wait, 600.
600.
That's
The
124.
cube root of,
So
the
Total.
square root of 600 is 24.5.
Where did you get 600?
24.5. So what you did was what? You did. So remember we have a squared plus b squared equals c squared. What are we trying to find? What letter? C, okay?
22 point.
We're trying to find C. So we need these two.
22.36.
22 point.
22.
So you got that by doing 10 squared is what? 100 plus 20 squared is what?
But Drew, how did we get to 200?
400, right? Equals C squared,
No.
right?
Yeah, this
So what's the next step?
Way low.
Hmm? 500, right?
the square root of 500 is 22.36.
Approximately.
22.36?
Yep.
36. Okay. So this is our first answer. This is our second answer. This is our third answer. Let's do a new slide. Do-do-do-do-do. New slide. Blank. There we go. And let's see what our next problem is. Uh-oh.
Video.
5 and move your silliness. Oh, shoot. I know. I can move it though. There we go. 5 to the left and 5 up. Now, wait a minute. We didn't put something in the last one. What's the last one missing? It's missing a vector arrow. Which direction was it going?
The bus south.
Down right.
Down and to the right, like this?
Yes.
Okay. So our next one was what? 5 and 5? Hold up. 5 to the left and 5 up. Okay, hold on. So we have 5 to the left, right? We're going this way. Oh, I should put that on top. I just was running out of space. Y'all know, trust me there. It's here. 5. And then the other 5 was going up, right? 5 going up. Let's do this way. Okay. So what are we doing? Equals C squared.
25.
25 plus 25 equals 50. We need the square root of 50. What is it? What? 7.07. Which way? Which way?
Northeast. Northeast. East.
Tip to tail. Tip to tail. One's going this way. One's going this way.
It's northeast.
That's what, well, okay. Are we saying this way? Is this what we're all trying to say? Okay. Well, let's see where we write. Where do we write? Oh, not that guy. Hold up. Wrong dude. This dude, same dude, different place.
Okay.
Full screen. Thank you. Okay, where do we write?
Let's go through. Connecting these first two tip to tail, I can see that 12 and 20 are just working together, so that overall vector is going to be 32 to the right.
Boom.
Connecting the second two tip to tail, this time they're working against each other, and so that new final connecting vector is going to be 4 pointing up.
Got that one.
This next set here, I'm going to connect tip to tail again, and I can see that when I draw that final vector from the tail of the first to the tip of the last, it's forming a right triangle. So if I use the Pythagorean theorem, I find this is equal to 22.36
We get that?
pointing down like that.
All right.
Finally, I have these two down here, and so if I connect them tip to tail, I find that it looks like this, 7.07 after I use the Pythagorean theorem.
What do you know?
And that's what you have to know about adding and labeling vectors.
Together.
What do you?
Cool. He's my miracle.
Don't know who you are. Go away.
Never heard.
Not my kid. So here's what we'll do. No, God, it's gonna be a sad. Oh, Iron Cold mom. Don't make this sad. Oh, it went away. All right, so let's do. I'll let you guys watch Professor Dave for fun. If you've been around for a while, you will find we love Professor Dave. He's our friend, especially for science, because he is just like absolutely the best, right? Oh, yeah, for chemistry, we eat up all the Professor Dave videos. So I'll put this on, and how many minutes is it? Hang on, let me tell you. Doo-doo-doo. So it's a 10-minute one. So listen up. So that means you're gonna have, you know, about 12 minutes when this is over, which gives you time to crank out Skittles. But what I want you to do is be sure that you have returned all your lab supplies when this video is over. Be sure you've returned it and look and remember, oh, I had 3 stopwatches and 2 meter sticks, and make sure they're actually there. Okay? Good with that? Also, for this group, because all my seniors are here, which means all my captains are here, right? All right, this is when you're going to need to use your forum. What's the word? Thank you. Gonna need to use your forum. I set up, and I'll put this in the email. I just set up a file in your Dropbox, and this is lab data in there. I set up individual folders for your teams if you want to share the document. So be sure that you make sure that your teammates, especially our newbies and our little newbies especially, that they know that they need to turn in a lab with everything on it, which means everything on the lab needs to be answered. The graphs need to be done. And then you need to write out that procedure. If you want to type up the procedure, great. If you want to just scan what you wrote, but procedure, remember, is written as steps. 1, 2, 3, 4. Be sure that you're capitalizing and spelling things right. You have time. If you have time to take something home and work on it, then it should come back nice, right? Like if you're making notes in class, I don't expect them to be beautiful. I may not even be able to read it. Some of you would not, you look at my college notebooks and go, what? Because I have a shorthand that I use, but I know what it means. If you're going to turn something in, make sure it is very clear. It looks good, right? Everybody can turn in the same lab, but I need one from everybody. All right, on your team, that is.
Okay.
So here's Professor Dave. When Professor Dave is done,
I want to tell you about that.
clean up and hit the road. Science, we love Professor Dave. He's the best.
We are always dealing with numbers. Big, small, rational, irrational, but numbers all the same. Now it's time to learn about another concept called a vector. This is a mathematical construct that has both magnitude and direction.
Oh, yeah.
The magnitude
right.
will be a number, so a vector can have a magnitude of 5. This is the part that tells us how much, but it also has a direction, meaning 5 of something in a particular direction. This is why we represent a vector with an arrow. The length of the vector tells us the magnitude, so a longer vector means a greater magnitude, and the direction the arrow points, relative to some axes, tells us the direction of the vector. Vectors are of tremendous importance in physics because they describe things like forces that cause the 3-dimensional motion of objects. You can check out some of the things we can do with vectors after this by checking out my classical physics series. But for now, let's go ahead and learn all the things we need to know about vectors in order to do more math.
This is a cluster full of orders you aren't buying.
Yeah.
MailChimp uses real.
Stupid ad. There
Many
you go.
vectors are simply displacement vectors, denoting how far an object has traveled
This
and
is what
in
we're
which
doing.
direction.
Right?
If such a vector connects 2 points, like A and B, we can call this vector AB with a
See,
little
label it
arrow.
that way too, which is different than
That's
with the
one
last
way
item.
to represent a vector. We can also just refer to a vector with a letter, like U.
Any letter.
Different vectors with the same magnitude and direction are called equivalent vectors. But of course, vectors can have different magnitudes and directions, and we can manipulate and combine vectors in various ways. First, there is vector addition. If we have vector U and vector V, and we place them head to tail, with V starting where U ends,
Tip to tail,
being
tip to
very
tail.
careful not to alter the direction of either vector, then the sum of these vectors, or U plus V, will simply go from the start of U to the end of V, forming a triangle, like so. If these vectors were AB and BC, their sum would be called AC, as it would connect A and C. We don't necessarily have to draw triangles, though. Let's say U and V start at the same point. let's duplicate u and v.
Here's where it
and
goes
move
beyond
them
what
so
we're
as to
gonna do,
form a
but it's
parallelogram
cool.
like this. Now the sum of the two vectors, u plus v, can be represented as the diagonal of the parallelogram.
Geometry.
So there are a number of ways to represent vector addition geometrically. We can also perform multiplication with vectors. The simplest way to do this is called scalar multiplication. This is when a vector is multiplied by a scalar, which is just a number. So if we have some vector u and we multiply it by the scalar 2, all we do is double the length of the vector, making it start from the same point, but reach twice as far in the direction it is pointing. So when multiplying a vector by a scalar that is greater than 0, we just multiply the length of the vector by the scalar. If the scalar is less than 0 or a negative number, we still alter the length of the vector in the same way, but we also reorient it to point in the negative direction relative to its original position, which is just precisely the opposite direction or 180 degrees away. So vector u times the scalar -1 will just flip it over in this manner to give us -u. This understanding will allow us to now perform vector subtraction. If we have two vectors, u and v, aligned as we did previously, how can we get u minus v? Well, u minus v is the same thing as u plus -v. So if we take v and flip the direction, it is now -v, and we can just do vector addition like we already learned. Completing the triangle with u and -v will give us u plus -v, or u minus v, and we have just performed vector subtraction. We can combine scalar multiplication and vector addition and subtraction to do all kinds of things with vectors, which we will see later. We should also note that vectors can be represented by components, which are kind of like coordinates. Let's say a vector extends from the origin to the point a1, a2. The vector itself can be represented this way, kind of like the point, but with this bracket-like notation rather than parentheses to distinguish the vector from the ordered pair that represents the point. This can be done in a three-dimensional coordinate system as well, with x, y, and z axes. The length or magnitude of a vector, represented by these brackets here that look like absolute value brackets, can be calculated by finding the square root of the sum of the squares of its components. We can also use this information to do more algebra with vectors. If we have a vector A with components A1 and A2, and another vector B with components B1 and B2, the sum of these vectors, or A plus B, will have the components A1 plus B1 and A2 plus B2. The same can be said for vector subtraction. We just subtract the corresponding components. In fact, let's quickly mention some important properties of vectors. The commutative and associative properties of addition apply to vectors, like the way that A plus B equals B plus A, and the way that A plus the quantity B plus C equals the quantity A plus B plus C. Any vector plus the zero vector, which is the vector with zeros for all its components, will simply give the same vector we started with. Any vector plus the negative version of that same vector, which is simply a vector minus itself, is the zero vector. While we can't add a vector and a scalar can be distributed across a sum of vectors, and a vector can be distributed across a sum of scalars. A product of scalars times a vector is the same as one of the scalars times the product of the other scalar and the vector. And 1 times any vector is simply that vector. Those are the important properties we should understand.
Does that look familiar?
No.
Those of you who've done
There is
algebra?
one other way we can represent
bit?
vectors that will be important to know, and it involves standard basis vectors,
Oh
which are
boy.
unit vectors, meaning they have a length of 1. If we are in a three-dimensional coordinate system, any vector can be represented by 3 components. The vector with the components 1, 0, 0, extending 1 unit along the x-axis, is denoted by a lowercase I. The vector with components 0, 1, 0, extending 1 unit along the y-axis is denoted by a lowercase j. And 0, 0, 1, extending 1 unit along the z-axis is denoted by a lowercase k. We can now represent any vector with multiples of I, j, and k. So 5, -2, 9 can also be 5i minus 2j plus 9k. This also works in 2 dimensions, we just lose the k.
Okay.
The reason this is useful
Zero.
is that algebraic manipulations can become much more intuitive, as operations like multiplying a vector by a scalar are reduced to simply distributing a number across a binomial or trinomial, which is trivial algebra. We can also add 2 vectors together without having to draw them. We can simply define one vector A, which we can say is equal to 2i minus j plus 4k, and another vector B, which is I plus 6j minus 2k. Then to do something like 2a plus 3b, we can simply change A and B to this other notation. First, we distribute each scalar across the sum it operates on. Then we simply combine like terms and we end up with 7i plus 16j plus 2k. And we have performed this complex operation using simple algebra. Now that we know how to perform a few different operations with vectors, let's check comprehension.
So he's got some more like physics level, but did any of that, like the commutative and associative stuff, look familiar to you? No, come on. If you've done algebra, it's familiar.
I have a test on this tomorrow.
Oh, okay. So when you're sitting there and you're doing your math homework and you're like, what the heck am I doing? What does this even mean? That's what it is. So let's do one more before I turn you loose to get everything straight. All right, let's say we have, let me make this a little smaller. Whoop, whoop. Let me go this way and let me make it a nice big purple color. Question. Did you have a question? Of course, you don't have to ask, just go. All right, so I'm gonna give you a point for asking. Yay. That's the only thing. Yes. All right, Milo, pick a direction since you haven't answered anything yet today. Right, left, up, down. Okay, we're gonna go right, and we're gonna say this is A. All right, pick in another direction. Down, okay, and we're gonna say down. We're gonna call this one. This is gonna be B. Okay, now. How long do you want A to be?
10.
Wait, Milo, I'm asking Milo.
And pick any number.
You can, because people have calculators, but I don't know if you want to be crazy. Pick something, just pick something between 1 and 20. 4 meters, okay. And it's gonna be to the right, and this one's gonna be, how much is B gonna be? Would, pick another, Milo. 5 meters, okay, so here we go. We're going 4 meters to the right, right? And then we're going 5 meters. This is not going to be just scale, but you're going to give me a break on that. Somebody tell me, what's our displacement? It's a vector. So what are we going to use? What's the theorem? Pythagorean theorem. What is it? Tell me. No. Tell me the formula. What's the Pythagorean theorem? What is it? A squared plus, that's an A. A squared plus B squared equals C squared. Okay. So what's it going to be? 6.4.
Which is square root of 41.
Okay. 6.4 what? Meters what? Oh, wait, this guy should be going down. I should have drawn it the other direction to make it easier. But which direction is this going?
From the way you have it driven it.
Yeah.
Southeast.
I should have done it the other way. Should have made him. There it is.
Yeah.
5. Okay. So, well, what we can say, kind of, we could say southeast if we want to pretend it's southeast. Good. You guys got it. It's so hard to write on this thing and make it clear because you don't see your letter till after you've written it. Okay, good. So you figured that out. You understand that bit? Okay, one thing. This is about the extent of the vector math we're going to do. So if you can do Pythagorean theorem, if you remember it, you'll be good to go. If you can do addition, multiplication, what's our, hang on. What's our, somebody describe our triangle to me. What goes where?
Distance on the top and speed and time on the bottom.
Right. So if I want to find D, what is that?
Distance divided by time.
If I want to find distance, okay. If I want to find time, D divided by V. And if I want to find V, D divided by T. Good. Okay. Keep that one in your mind. As we progress through the next couple units, or this unit, and I think next unit too, there's a lot of these. Okay. And they're really helpful because if you can picture the triangle in your head, you don't have to remember every single formula. You can just see it. There it is. Right. Side by side is multiply. On top is divide. Does everybody know order of operations?
Yes.
Okay. Next week, you're going to need it. Refresh your brain. Yeah, it's please excuse my dear Aunt Sally, but there's a part people forget. And it causes this problem. So the part that people forget is that it's left to right, but that applies to, so what's the please is what? Parentheses. What's the excuse? Right. What's the M? My multiplication. That's an actual X. And what's the D? And what's the aunt? And addition. And what's subtraction? Okay. Left to right. That means these and these. You do multiplication and division from left to right, whichever comes first. If division is first in your problem, you don't go, oh, dear comes after my, so I do division second. Nope. Left to right, left to right. A million of these on social media, some stupid 7th grade math problem, and full-grown people argue over it for days and comment 1,000 times as to why everybody's wrong, because this is the part people don't get. So it's please excuse my dear Aunt Sally's last remarks. Woo, she was ugly before she died, or left, whatever it was, died or disappeared, left the building. Okay? All right, make sure you have all your lab supplies back on your tray. All righty? And you can hit the Skittles machine. I'll put these out where you can reach them. Just turn them around so you can reach stuff. Here's one.
Push them out of your way.
Yeah, for real. There he is. I love my new apple. Look how cute it is. Isn't that the coolest? Look at that. I like my apple.
When you're done, I'm telling the group something, so if you'll just wait a minute.
Okey-doke.
And then.
Yeah, actually, he was getting most of the answers fast. He answered some of them first. No, I'm just saying, it's good.
Yeah, read the get to the document I'm posting. So it's just going to be our team name, so team, and then, all lower.
What image creator website were you using?
What now?
What image creator website were you using?
Oh, ChatGPT, just Bing. It does DALL-E. Yeah.
You can't download it, but you can use my answers.
Lucas. Lucas, can I have your coins?
And you guys do have a Dropbox file that you can use for putting stuff anywhere you need it. I created one for you. You good to go?
Just posted since I'm doing it in a Word doc.
Yeah.
I just posted that.
That works too. Perfect. There you go.
So I'm just making sure that everyone knows that.
Yeah, you're good. Oh, Bailey, you want your
Yes, but I will be right back because I went to see you about something.
Yeah, sure. Is that one in here? Stop this.
Well,